In our last video, we saw how robots calculate where their hand is using joint angles, a process called forward kinematics. But what if we know where we want the hand to go, and need to find the joint angles that get it there? This reverse calculation is called inverse kinematics, and it is crucial for robotics, character animation, and game physics. For simple robotic arms, we can calculate the exact joint angles directly using basic geometry. First, we draw a target line from the base to the target coordinate. We project this target point to find its horizontal displacement x and vertical displacement y, and use them to calculate the straight line distance d via the Pythagorean theorem. To solve for the joint angles, we must construct them geometrically. We start by finding the internal angle alpha of the triangle formed by the arm lengths and the target line. Since we know the lengths of all three sides L1 is L2, and the target distance d, we calculate alpha using the law of cosines. Next, we calculate the angle beta, which is the direction of the target line relative to the horizontal axis, computed using the arctangent of y and x. With alpha and beta determined, we construct the shoulder joint angle θ1. By subtracting the internal angle alpha from the target direction angle beta, we position the first link and elbow joint. To calculate the elbow angle, we look at the internal angle gamma of the arm triangle. Using the same law of cosines, we solve for gamma using the link lengths L1, L2, and the target distance d. The physical elbow joint angle θ2 is the exterior angle, representing the bend relative to the extension of the first link. Because gamma and θ2 form a straight line, we calculate θ2 as 180 degrees minus gamma. This construction is universal. Whether the first link is longer, shorter, or equal to the second, the same law of cosines approach correctly calculates the joint angles, as long as the target lies within the arm's reach. While this analytical solution is fast and exact, it becomes incredibly difficult to solve as we add more links or work in 3 dimensions. To solve inverse kinematics for complex arms, we use numerical methods that iteratively guide the joints closer to the target. One of the most elegant and visual numerical algorithms is FABRIK, which stands for forward and backward reaching inverse kinematics. First, we begin the backward pass. We start at the end effector and place the hand directly on the target coordinate. Next, we slide the wrist joint along the link direction pointing toward the updated hand, maintaining its constant segment length. We then repeat this step for the elbow joint, pulling it along the segment direction toward the newly updated wrist. Finally, we pull the shoulder joint toward the updated elbow. Because the shoulder is now disconnected from its base origin, we need a forward pass to fix its anchor. To start the forward pass, we snap the shoulder joint directly back to its fixed base origin. We then push the elbow joint outward along the link vector pointing toward the updated shoulder, restoring its correct length. Next, we adjust the wrist joint outward along the segment line from the newly updated elbow joint. Finally, we push the hand joint outward along the forearm link. This completes the first full iteration, leaving the hand slightly off target but much closer than it was initially. By repeating this backward and forward loop just a few times, the arm quickly converges until the hand rests exactly on the target. Both analytical and numerical methods have unique strengths depending on the complexity of the robot. Analytical solutions are ideal for simple, fast-moving limbs, while numerical solvers like FABRIK are perfect for complex creatures and characters. First, closed loops are solved by breaking them into separate serial chains and averaging the position of shared joints to close the loop. Multi-effector tree structures are solved by propagating coordinates back from each finger, averaging the results at the junctions, and then pushing them forward from the base. Combining these rules allows us to solve hybrid closed-loop and branch topologies in real time, all using the exact same simple distance projections. If you want to see how these algorithms look in code, check out the links in the description and subscribe for more robotics guides. Thanks for watching.